Hey everyone, good morning. Welcome back to our lectures on optimization and dynamics. So today we're going to look at a second example where we're going to use DAP-BC to perform some sort of an optimization on a system. So we once again integrated the dynamic queue optimizer into the DAP-BC workbench in one of our previous lectures. I think it was actually the previous lecture that we had where we looked at that. So today we're just going to use the standard DAP-BC dynamic queue hybrid workbench that we've now deduced to actually perform that application example. Now, before we do that, I just want to give you a quick review of everything that we've done up to now. So firstly, we just started off, and this is now under the optimization and dynamics study theme specifically. We first started off just looking at the introduction once again of the DAP-BC workbench. We mentioned that it is a numerical workbench, and we do have those scripts available. So this allowed us to integrate some sort of an optimizer into the dynamic analyzer. And the optimizer that we focused on over there was the dynamic queue gradient-based optimizer, which is an extension of this ALFOP-C algorithm that was developed by Snyman back in 2000. And the general form of that optimizer is also given over here. We minimize some sort of an objective function subject to a set of constraints, and then also lower and upper bounds. And then if we have a move limit, we also have to specify that. So in regards to that, we then moved over to the optimization only examples, and these examples focused specifically on analytical functions, so functions where we explicitly had the objective function defined. So we could easily go and find the gradients over there using the analytical gradient matrices that we have over here. Now, we did mention that if you don't have these analytical functions available, then it means you'll have to use some sort of a central or a finite difference method, whether it be forward difference, backward difference, or central difference method to go and calculate your gradient vectors and matrices. So the problems that we had over here, example problems 1 to 3, were different complexities. So firstly, we just started off with example problem 1, which focused on a single design variable or simply a single variable objective function. And we could easily go and validate where the minima on this graph was placed. We also said that depending on where you start your initial design, the gradient-based dynamic queue optimizer will also optimize to different minima. It will not necessarily reach the global minimum. In order to find the global minimum, you'll have to test different initial designs and see which one is going to give you the smallest value over here. And then example problem 2 was simply a 3D graph that we had over here. So it was also fairly, it was still fairly easy to validate on a graph where our minimum point sat. But then example problem 3 had 4 design variables, so x1 up to x4. And in this case, we could not rely on some graphical validation method over here. So we had to make use instead of something like dynamic queue to instead give us hopefully a good answer with regards to our optimized design. And we could go and check whether the optimization terminated successfully by just looking at the convergence behavior as well. We know that we can get those convergence histories directly from the dynamic queue outputs. So with all of that in mind, we then extended the dynamic queue optimizer to the DAP-BC. We also looked then at an optimization procedure, or actually 2 of them. So the first one was simply integrating DAP-BC into dynamic queue. Once this first set of procedures are done, then we can use the DAP-BC dynamic queue workbench to go and perform these problem-specific procedures as well. So defining the parameters, the objective function, making sure that we define all of our variables correctly in the respective script, and then running the optimization.m file to obtain the convergence or the iterative-based optimization solution. Then we moved on to the application examples as well. So we first looked at a driven pendulum rod subjected to a constant torque. And we had a few design variables over here. I think it was 4 design variables that we considered. we followed the optimization procedure, and we obtained the final design variables with respect to all of the constraints. In this case, we wanted to maximize the acceleration. So since we're working with a maximization problem, all that we had to do was multiply our objective function by -1 to turn it into a minimization problem. And in this case, we also had an equality constraint that we placed on the speed of the system, or the velocity magnitude, that had to be 20 meters per second as the maximum value. And we can see that it did terminate after 3 seconds at 20 meters per second. So that gives us confidence in the values that we obtained. Then we also just defined the initial design angle, or the orientation angle of the pendulum rod. So this is just shown over here from the animation pane. And that was also one of the optimized, or the design variables that we considered over there. So today we are then going to move on to section 6.2, or rather the section 6.2 in this mind map. It doesn't correspond to 6.2 in the PMD textbook, but this one focuses on the card subjected to an aerodynamic and torque load. So previously we looked at the card where we had a card body 1, and then we had 2 wheels, the rear wheel body 2 and front wheel body 3. And we essentially want to reconsider the card model given over there, and we want to perform some optimization over there. So the forward dynamics problem that we looked at was proposing a relation for the torque and measuring the angular characteristics of the wheel and the card body. So this figure over here is from the PMD textbook for the standard example that we did. The solid line over here was where we had no resistive forces, and the dashed line is then with resistive forces. And this was specifically the aerodynamic load that we considered. Okay, and we then also, I think, had this plot, which was also, I think, for one of the wheels. I think it was the rear wheel angular velocity. And in this case, we can see that it's negative, so it corresponds to a horizontal velocity of being positive. We know that if the wheel is moving clockwise, we expect the card to move to the right. So if we have a positive horizontal velocity, we expect a negative angular velocity. Okay, so we once again expand on this application by considering a few design questions. Firstly, how would the maximum specified torque influence the acceleration of the card body? And what is the influence of the aerodynamic drag coefficient on the speed of the card? And we can use these questions to then formulate a rather simple design problem where we ask, we want to maximize the acceleration of card body 1 subject to the torque applied to the rear wheel. And this actually refers to the maximum motor torque that we want to apply, and the aerodynamic drag coefficient as well. And a few design considerations is then the maximum time of motion that should be taken as 6 seconds with a reporting time step of 0.1 second. And then the torque should not exceed 50 Newton meters. So there we have some sort of an inequality constraint that we specify over here. And the card should achieve a maximum allowable speed of 1.2 meters per second during its motion. So this is an equality constraint that we're going to apply on the system. Okay, and then of course our objective function in this case is maximizing the acceleration of the card body. Since it's a maximization problem, we're just going to multiply it by -1 to turn it into a minimization problem. Torque applied and the aerodynamic drag coefficient are our two design variables that we're going to work with. So following the optimization procedure, we can start by first identifying and defining our objective function as well under the post.m file. So over here it was just given as max underscore ACC, which is then equal to the maximum absolute value of your x acceleration. So this is simply the acceleration of the card. So across all time steps for body 1 in one direction, which is the x direction. And if have to remember to also update the folder name. So previously we were working with, I think it was PR_D. In this case, we just want to change it to cart_D. And we now change it directly in the dap.m file, since we're not going to give it any input in the command window. All right. Now, with that being done, we can then define our design variables as well, and we want to assign an index to each of them. So what I've done over here is just call x1 the maximum motor torque, and then x2 will be C-aero, or the aerodynamic drag coefficient. Once this is set up, then I can define these design variables in the corresponding dap.bc input files. And since I'm now working in the dap.bc input files, I need to remember to use x_dap when I denote any of these variables. So if I go to, in this case, I think it's user force that we're working with. So most of this is stock standard. I just changed the T max equal to, and this had some value over here. In this case, I just changed it to x_dap1, and then the aerodynamic damping coefficient in this case is then x_dap2, which corresponds to the indices that I defined in the mind map. Okay, then I just have to ensure that x_dap is also defined globally under the formulation. Some files include global script as well. So if I go to formulation, some files include global, I can see that x_dap is indeed defined over there. So that ensures that my variables over here are globalized, so that if I call x_dap in one of the input files and I still need it in one of the other input files, then it carries over. I don't have to worry about redefining it in another function. Okay, then for step 5, we just need to define the equality constraint pertaining to the speed. So we said previously over here, the cart should achieve a maximum allowable speed of 1.2 meters per second during its motion. So in order to get this out, I'm simply going back to my post.m. Since I'm working with a result from the dap.bc now, I define my max speed value over here. And this will simply be the maximum value of the square root of the x velocity squared plus the y velocity squared. In this case, I could have probably gotten away with just defining in the one direction, since the cart body will in any case just move in the x direction. So you could have actually taken out this part over here. So if you perhaps wanted to write this, let's say, as max speed value equal to maximum absolute, and then you just call this RD11, that would also have been fine. Okay, so both of these are interchangeable with one another. For this case, I'm just going to rely on the previous statement that I had. Once this is now defined, now I just have to go over to my transition script. So this is now the minimizer inputs.m file that I have. And I now have to express the objective function and any implicit constraints. In this case, it's the equality constraint that I just have to give over here under minimizer inputs. So since I'm now obtaining this result directly from dap.bc, I'm going to define that equality constraint under minimizer input. So if I open this one up, so most of this is once again stock standard. All of this add path include global x_dap, dap and post you can leave as is. The objective function is now the one that I just have to go and define depending on the variable that I specified in post.m. In my case, it's the maximum acceleration value. I want to maximize that, so I have to remember to add the minus in front. And then for the equality constraint, I just named this h1, and that is simply the maximum speed value that I also get from post.m, and I just minus 1.2 from that. You could have also changed this to, I think 1.2 minus max speed value. It doesn't really matter since it's an equality constraint, so it should in any case equal 0. Okay, now once that is done, then we just need to now move over to our dynamic queue script. So the fch.m script is then updated in accordance with the minimizer input script, and then we can just check whether the grad fch file is still going to give us, or is still using the appropriate parameters over here. So if I open up dynamic queue and I go down to fch.m, then you'll see over here I say if h1 is equal to minimizer inputs x. In this case, I'm now just using x, not xdap, since I'm working with the dynamic queue files. And then I can just go and say h in brackets 1 is equal to that h1 that I also extracted from the minimizer inputs transition file. Then I also have to go to grad fch, just make sure that I'm still working with the correct parameters. So in this case, I'm still using the forward difference method. The delt x equal to 10 to the power of minus 8 is fine, or it's deemed appropriate for this problem. So yeah, it basically carries over all of the difference, the finite difference method that we had for the previous example. So this should be fine. Once that is done, then I just have to go and update the optimization.m file, which is updated to include all non-default inputs, starting points, tolerances, and boundary conditions. Okay, so in this case, I just have to go and define my new starting position. So if I go to optimization.m, I now chose x1, which is the maximum torque, to be 20, x2, which is the aerodynamic drag coefficient, as 5, and then I just group all of that together in a list. Then I also have this upper boundary condition, and you'll remember from our definition that we had over here, we said the torque should not exceed 50 Newton meters. So I can go over here, and just apply the upper boundary condition to x1, and that is then a maximum of 50 Newton meters that I specify over there. Then I can go and group all of this together in this dinq command that I have over here. So initial design, I don't have any lower bound, so I'm going to leave this as an empty list. Then I have my upper boundary condition that I give, and this 60 then pertains to the move limit. Now, to calculate or to get a good idea of what your move limit should be, we can once again go back to, I think it was the example problems that we looked at. So if I scroll down, you'll see there's this word icon over here. So if you click on this one, it should open the file. And under the inputs that you can give, it says DML is the move limit, which should be approximately the same order of magnitude as the radius of the region of interest. And we can calculate this as the square root of the number of variables that we have multiplied by the maximum variable range. So in our case, we have an upper bound on the maximum torque. We expect that this is probably going to give us a good idea of what your maximum variable range is going to be. So if I go to the command window, I can do a quick calculation over here and say the square root of 2, since I'm working with 2 design variables, multiplied by, let's say, perhaps 50. Then I get this value of 70.7. Now, I used a move limit of 60, which is also fine. It's still the same order of magnitude. So I expect that this should converge fairly quickly. In this case, if I were to use a move limit of 1, so I perhaps don't specify it, or I just use, or I say DML must be equal to 1. Essentially what that would do is, depending on where your initial design is situated, it's going to take very small step sizes to reach the optimum design. So you might have to run, let's say, 100 iterations or something like that to get your answer. Instead, if I'm careful with the selection of my DML, I can reach an optimized solution much quicker. Okay, so in this case, 60 should be appropriate. Now, if I go clear or close all CLC, I just have to make sure that I now updated everything in accordance with the procedure. Okay, so now they say the optimization can simply be executed by running the optimization in the command window. So over here, I'm just going to type optimization. Okay, so I think this one runs fairly quickly. It takes about a minute or so. And we Now note that we only have 2 design variables in this case. For the previous example, we had 4 design variables. So it was significantly more function evaluations as well that we had to perform over there. And then we also had to perform a gradient calculation for each of the design variables. In this case, it now terminates or runs fairly quickly. So yeah, I think the next iteration should stop it. Right, so we can see over here as well with iteration 5, it reached a fairly good solution. In this case, it was 10 to the power of minus 5, but because I specified a fairly small convergence tolerance, or I just used the default tolerance of 1 times 10 to the power of minus 5, it struggled to converge over here. So now it's just moving towards I think a solution once again. But if I were to use a convergence tolerance of 10 to the power of minus 4, it would have probably terminated after 5 iterations. Let's just see where it goes from here. Right. So if I look at the convergence, I can see it took 17 iterations and about 2 minutes to converge. If I look at the equality constraint as well, I can see that's 10 to the power of minus 10, so essentially 0. And then the inequality constraint, or in this case, it's the side constraint, an upper boundary condition is 10 to the power of minus 8. Which makes sense. I expect to get a maximized acceleration if I make my maximum motor torque as large as possible. And then the aerodynamic drag coefficient in this case is 15.6. And this is mostly due to the fact that I need a maximum velocity of 1.2 meters per second. So if I didn't specify the maximum velocity constraint, I would probably get away with a 0 value on the aerodynamic drag coefficient. Since, yeah, so then there's nothing really limiting the velocity. Okay, and then, yeah, so just another thing that I should perhaps note, and I see this is now a difference with the Octave versions as well. Currently, I'm working with the Octave 6.4, so it took about 17 iterations. With Octave version 9.2, the one that I tested with yesterday, it seemed to only take about 11 iterations or so. So there does seem to be a difference in the solving method used by the different versions of Octave. I don't really think it's a major difference, but it might influence your analysis time. But other than that, yeah, so most of the results are exactly the same. I mean, I also got 50 and 15.6 at the end. So it's just a matter of how long it takes to actually solve the problem. Now, if I look at the objective function history, I can see in this case there does seem to be these spikes in the data as well. So it's not the best convergence behavior, but the fact that I did get converged constraints or no constraints violation at the end means that I at least solved the problem or adhere to the system properties that I specified. If I go to the variable history as well, once again we can see this sort of oscillatory or spike data over here as well. Then for the inequality constraints, once again the spikes, and then lastly for the equality constraints, we can perhaps see a bit of a better convergence behavior over here. We can actually see from iteration 12 to 17, it remains more or less constant over here. Yes. Yes, I think you can. You can. Yes. Yes, yeah, so that would probably work. So if you decrease that delta x value in your grad FCH file, then you might actually see that it converges closer to iteration 5. We can see that it's fairly close to that. It was 5.5 times 10 to the power of minus 5. So if you make those step sizes smaller, then it will actually be able to take smaller sampling points, yes. Another thing that you can perhaps do is just to play around with your convergence tolerances as well. So if you want to use 10 to the power of minus 4, you might also get a bit better convergence or a bit sooner convergence over there as well. Yes. All right. Okay, so I think that is then so that's the results from the dynamic Q output that we wanted to get. Just want to check if I have the graphs over here. Okay, yeah, so you can go ahead and plot the accelerations, velocities, and everything as well. I already did it over here. So the optimized design variables in this case is then 50 Newton meters and 15.6 Newton seconds per meter for the respective maximum torque and the aerodynamic damping coefficient. If we look at the linear acceleration, we can see that the maximum is around 4. And this makes sense if I go back to my command window and I just type in F. The value that it gave me out is minus 4.0323. So I just have to remember to multiply this value by negative 1. Since I changed it to a minimization problem, I now just have to change it back to a maximization problem. So 4 meters per second square is then the maximum that I can reach. And if I look at the rotational acceleration as well of the, so this is of the rear wheel, I think. And in this case, it also starts off negative, and then at some point over here, it then reaches 0. So that tells me that there's some sort of a maximum velocity in the system that I reached. So if I look at the velocity curve, I can see that indeed it does start at 0, and then over here at around 2 seconds, it then plateaus out to the equality constraint value of 1.2 meters per second. Okay, so from a graphical perspective and a dynamic analysis results perspective, I can see that the optimization does give me a good feasible design. All right. So I think that's more or less the results that we wanted to get over here. Let me perhaps just check if we change now the convergence tolerance on the step size, what would happen, or on the this one over here. So I'm just going to let's make this one 1e minus 4 and 1e minus 5. So this is just for the x norm and then for the f norm. So we can first see what this one is going to do. Right, so I do expect that there's going to be some deviation from the previous iteration values. The reason being your dynamic Q optimizer uses the alpha-C algorithm as a sub-algorithm. So what essentially happens is if you specify a convergence tolerance of, let's say, 10 to the power of minus 5 on one of your, well, in this case, it was the X norm. What the alpha-C algorithm does is it then takes whatever you specify as your convergence tolerance and multiplies it by 10 to the power of minus 3. So if I specify 10 to the power of minus 5, it's going to use 10 to the power of minus 8 for the alpha-C algorithm. And if I use 10 to the power of minus 4, it's going to use 10 to the power of minus 7 in alpha-C. So you can go and change this manually, but it's better to maybe just on a global level control the values of your dynamic Q optimizer. Okay, so this one terminated after 6 iterations and obviously on the RFD in this case, but we can still see it's around 50 and 15.6. So we get exactly the same results. And we can see that the inequality constraints in this case, they are still fairly close to 0, but previously we had 10 to the power of minus 10 on H1. So there does seem to be some compromise on the accuracy of this method, or this choice of convergence tolerances. Okay, so if I now perhaps go and check what happens to the step size, so I'm just going to leave these two out. Right, so this one then took one less iteration to solve. This one took 5 iterations, so also terminated on the RFD value. We once again get 50 and 15.6. If we look at the, so in this case, the equality and inequality constraint values are actually now closer to 0 than what we had initially when we used the 10 to the power of minus 8 step. And that also makes sense. We're now working with a tighter accuracy. Okay, now, just the last thing that I also want to point out, and this is something that I said in the previous lecture, which was not quite correct. With regards to the calculation of the gradients, I think I said that if you have something like, let's say, 2 design variables, then 3 function evaluations are going to be performed for each iteration. So it's actually 4 function evaluations, and for that we need to go to the dynamic queue analyzer. So if I go to DynQ over here, and I just type in FCH over here. Right, so you'll see it runs, you just go down. So firstly, if you don't specify the number of inequality and equality constraints that you have, for the very first iteration or iteration 0 that it's going to perform, it's going to create another function evaluation. So in that case, if you have 2 design variables, it's actually going to run 5 times. So it first has to determine the number of equality and inequality constraints that you have. Now, for the general iterations that you perform, so iterations 1 onwards, it first runs to determine the function values. Then it runs grad FCH, but under grad FCH, you'll see that it runs FCHX again. So that means it calculates the objective function again in this step, and then it only calculates the design variable values. So you start off with a function value calculation, and then you calculate the function value again under grad FCH, and then you perform its gradient calculations. So if I have, in this case, 2 design variables, then it's going to run a total of 4 times. Okay, so it's maybe not that performance intensive when you consider this type of problem that we have over here, but once you work with very complex multi-body mechanisms, 7, 8, 10 bodies or something like that, then you are going to notice that initial or that additional function evaluation that you perform is going to take a bit more time to solve. All right. So I think that is then everything for this example. Are there any questions with regards to this? Okay. All right. So so this then wraps up our application examples section over here. Then just a few concluding remarks that I also want to make. So the effectiveness of the dynamic queue optimizer is greatly underpinned by the performance of DAP-BC. And we mentioned this previously as well, the number of design variables that you have, depending on how complex your objective function is, the complexity of your constraints, and then discretization of input parameters as well. So something like your reporting time step. If you use a very fine reporting time step, the post processor or the post.m file is going to run a bit longer as well. And then data noise and discontinuities. We said if you have noisy data, then you have to use some sort of a filtering process. Just make sure that you get some smooth curvatures in your data as well. And then discontinuities, of course, as well. If you have a sharp edge where close to where your minimum is going to be, the system is also going to struggle to converge into that discontinuity. But all of these things are essentially going to influence the effectiveness and the performance of the dynamic queue optimizer. Now, the optimizer itself will also have an effect on the solution times. So firstly, the convergence tolerance. If you use too fine a convergence tolerance, it's going to take significantly more iterations to solve the problem. The variable ranges and the move limits as well, especially the move limits that we spoke about. So if you start fairly far away from your initial design and you use a very small move limit, it's going to take many step sizes to actually get to your optimized solution. The finite difference approach that you use can also have an effect. So the forward and backward difference method should take more or less the same time to solve. But if you were to use something like the central difference method, it means that you need to combine a forward and backward difference method to solve the problem. And in that case, it's going to take twice as long to solve the gradient for each variable. And then lastly, also the step size and the parameter sensitivities. And we now looked at the sensitivity, that delta x that we changed. So using 10 to the power of minus 9, it terminated after 5 iterations, where if we use 10 to the power of minus 8, it took about 17 iterations. Okay, and yeah, so that's then with regards to the step size. Just to point out, with regards to the parameter sensitivities, if you are interested in the sensitivity analysis, under the Aerodynamic, there is this sensitivity analysis.m file over here. So you can go and update this thing, but basically what it does is it just calculates, or it uses a delta x that you specify, and you essentially calculate the gradient for each of these. And what you should be able to get out, and I'm not sure if I have it plotted over here. Yeah, let me maybe see if I can find an example of that. Right, so this is more or less what you expect to get out when you perform a sensitivity analysis. So these are the different step sizes that I can test. For each of them, I calculate a gradient based on the objective function. And what you'll see is you have this increase in the value over here, then it basically makes a spike over here, and then it settles over here. Not necessarily at 0, it's just because I'm working with 10 to the power of 10 over here that I get these large deviations, but it should give you a sort of a constant line over here. And anywhere along this constant line, you can then go and select your step size value. So that's why in this case, it was 10 to the power of minus 8. So it's more or less in line, or more or less in the center of this constant line that I have over here. If I can go a bit finer, that's also fine. So 10 to the power of minus 9, minus 10 is maybe stretching it a bit. It's quite close to the increase in the value over here. Right, so we won't expect you to perform a sensitivity analysis for MSD 780, but if you perhaps want to use this for one of your projects, you do have the sensitivity analysis file available. Okay, so if I now just go back over here, yeah, so that's then the sensitivity analysis.m file that you have. Okay. So in general, a good balance must be found between the accuracy of your solution and the performance of the optimizer. The finer your tolerances are, the longer you will have to wait for a solution. Now that is, I think, self-explanatory from the examples that we did. Okay, so that then also then concludes the optimization and dynamics study theme that we wanted to look at. There is still one example that we're going to do, and that's then going to be the exam that we're going to run through. I'm going to do that in the next lecture. I'll also post the previous exam on ClickUp, so you'll have the exam and the paper available as well as the memo code. So you can work through that before we jump into that next lecture. Yeah, but that then concludes this part. Are there any questions? We move on. Okay. All right, so then I just quickly want to discuss assignment 2 as well, just with regards to what I expect over there. So you should see this available under the assignments content area on ClickUp. But the description reads, use the provided DAP-BC Dynamic Queue Hybrid Workbench revision 1, which is also available on ClickUp, to simulate and optimize one or more features of a planar multi-body mechanism of your choice. Now, if you decide to opt for a single feature, rather do something that is sufficiently complex. So don't go and like optimize the mass of a link in the system. It's fairly, I think that's fairly trivial. If you're trying to maximize the acceleration of a system, and you try to optimize the mass, then of course the system is going to try and make that mass as small as possible, so you get a large enough acceleration. So rather use something like the configuration of your mechanism and see how you can play around with that. Like I said, you can use one or more features. Preferably more features is better. It adds to the complexity of the optimization, and it also highlights the importance of the optimization. If you use 3 or so design variables, it's going to make more sense to do a dynamic queue optimizer. If you have a single design variable, you can basically just plot that as a function of your your objective function as a function of that design variable, and you can go and find that analytically, the minimum in that case. So rather opt for something that is a bit more complex. With regards to the mechanism itself, you're more than welcome to use the mechanism you did for assignment 1. If I did give you feedback, maybe just try and incorporate that before you move on to assignment 2. But overall, I think most of the mechanisms that I saw are pretty complex, it can be expanded upon fairly easily. So you should be fine with using that for assignment 2. So then, just as usual, you may not use one of the examples for which the input files already exist. Today I'm also going to upload then the exam code, so don't use that mechanism either. Try to find your own complex multi-body mechanism. All right, so then for the submission document, so it's just your input files again for what you used for assignment 1. Just going to expand that for assignment 2 then, include all of the design variables. User func, user force if they are applicable, and then you also have your dynamic queue files, so the fch.m, grad fch.m files, and then your transition script as well, minimizer inputs.m. And then any additional MATLAB files that you have modified. So if you want to, you can also include something like the dynamic queue.out file. So this is simply where it writes everything to so this is where it writes your iterations to a file. So you can also include something like this if you want to, or you can just discuss this in your actual report. And that is then the second submission document that you need, a PDF report, no longer than 10 pages. And you have to include, interpret, and validate where applicable the dynamic analysis and optimization results. So my suggestion for the interpretation is that you do an initial design and then compare that to the optimized design once the optimization is done. You can also include, I think, the convergence histories. So perhaps a discussion on what happens to the objective function, the design variables. Do you see good convergence? What happened to the inequality and equality constraints? All of those kind of things. Okay, so that then brings us just to the rubric. It remained more or less the same as what you had for assignment 1. Once again, the mechanism complexity is a multi-body mechanism consisting of 4 or more bodies or links, different joints that can be utilized as well. And then under mechanism complexity, I'm just going to consider the optimization complexity as well. So like I said, you are more than welcome to use a single feature. Just make sure it's a non-trivial feature that you're going to optimize. If you use more than one feature, that is also fine. Then for the evaluation of the performed dynamic analysis or analyses, I once again want to see the kinematics and dynamics in your analysis. You perhaps don't have to go into so much depth as you did with your first assignment, but I do want to at least see that you did consider the dynamics of the system together with the kinematics. And then lastly, for the interpretation and validation of the results, an in-depth interpretation of the results is presented with many visualizations and critical discussions. Like I mentioned, this will mostly focus on the actual optimization and then doing a good comparison between your initial and optimized design. And then also some validation or sanity checks in the simulation or optimization results. So you can perhaps decide to do this on your initial or your final design and see if the values that you get out do indeed make sense. Okay, but that's more or less the crux of assignment 2. So I don't think it should be too difficult. So any questions on this? Right. Okay, so I think this then wraps up everything that I wanted to look at in this lecture. So next lecture, we will then look at the exam, work through that, and then we'll see for the last lecture, I'll probably do maybe like an online Q&A session. But for now, we're just focusing on the optimization and getting a good idea of what the exam is also going to look like. All right, but then I'll see you again in the next lecture. Thanks.